In this lecture video, we continue the development of a multiple regression model based on the data in the delivery time dataset. Now, in our previous analysis where we tested the significance of the overall model, we concluded that at least one of the two slope coefficients, beta 1 or beta 2, is non-zero. A natural follow-up question would be, which of those coefficients are indeed non-zero? We're going to perform a follow-up test where we test the null hypothesis that beta 2 is equal to 0 given that x1 is in the model. Now, as we've seen in the notes, there are several equivalent ways of doing this. Equivalent in the sense that they give the same result. However, they differ in terms of how the procedures are actually carried out. So with that in mind, in this lecture video, we're going to perform this hypothesis test using a t-test that is based on the point estimate of beta 2 as well as its standard error. The software package that we're going to use is SAS Analytics Pro, and we're going to show how to obtain the values for the calculations using PROC IML as well as PROC REG. So let's take a look. All right, so let's look at example 4 in the textbook. Now, we've tested the significance of the overall model in the previous example, and we concluded there that at least one of the two slope coefficients is non-zero. A natural follow-up question is, which slope coefficients are non-zero? Now, in this particular example, we're going to test whether there is sufficient evidence in the data to conclude that beta 2 is different than 0, given that x1 is in the model. So this is going to be a conditional test conditioned on x1 being in the model. And so the null hypothesis would be that beta 2 is equal to 0, given that x1, which is the number of cases being delivered, is in the model, against the alternative hypothesis that beta 2 is not equal to 0, again conditioned on x1 is in the model. Now we're going to use a t-test to perform this test, and as you'll recall from your first methods class, that the form of a t-statistic is a ratio, the numerator being the difference between the point estimator for the parameter we're testing a hypothesis about. So beta 2 is the parameter we're testing a hypothesis about, and so I'll use beta 2 hat to represent the point estimator. And then we subtract from that the hypothesized value of beta 2, which in this case is 0. And then we divide that difference by the estimated standard error of beta 2 hat. And let me correct this right here. So yeah, and now we have that how we want it. Okay, so we're dividing that difference by the estimated standard error of beta 2 hat. Now, that's how we calculate the test statistic. The rejection criterion is to reject the null hypothesis if the absolute value of t-calc is greater than the upper alpha percentage point of the t-distribution with n minus p degrees of freedom. Now, in this case, n is 25, p is 3 in the unrestricted model, and so we would have 22 degrees of freedom for this test. Now, there's also an f-test version of this, and it's basically just squaring that test statistic, the t-calc test statistic, and that gives us the f statistic. And then if we were going to use that, then we would reject the null hypothesis if f-calc exceeds the upper alpha percentage point of the f distribution with 1 numerator degrees of freedom and n minus p denominator degrees of freedom. Now, in this case, the numerator degrees of freedom is 1 because there's only one restriction in the null hypothesis. There's only one parameter that we're testing a hypothesis about. And let me also say that in the rejection criterion for the t-test, we are rejecting if the absolute value of t-calc exceeds this upper percentage point because this is a two-tailed test. Now, we could certainly perform a one-tailed test, and if that was the case, then we would not take the absolute value of t-calc. All right, so let's scroll down and take a look. And in this first analysis, this first approach, we're going to use PROC IML, the interactive matrix language, to perform the analysis. And what I'm going to do is I'm going to append the required calculations for this follow-up hypothesis test to the previous program where we tested the significance of the overall model. And so we're not going to spend any time looking at the contents of the top portion of this program because we've already seen it and spent time with it. But I am going to go down to the very bottom here and show how to do the additional calculations required to perform this test involving beta 2. Now, what we need to do here, in fact, let me, I think what I'm going to do here, I need to move this. So I'm going to move it down here. I don't have to do it, but it just makes it flow better. And so we need to calculate the covariance matrix of the beta vector. So you'll remember that beta contains, or in the model, beta is the parameter or the vector of parameters, the beta parameters. And that vector is unknown, so we have to estimate it. And we have done that up above, and we called that estimated vector beta hat, beta hat, all right? And what we need here is the covariance matrix associated with that estimated vector. And so we're going to call that covariance matrix beta hat cov. Now, you'll recall from the textbook that the covariance matrix for beta hat is given by the point estimator for the variance of the error term in the model times the x prime x inverse matrix. Okay, and so that's the calculation that I'm doing here. I am constructing this 3x3 covariance matrix for beta hat. And you'll also recall that the point estimate of sigma squared, which again is the variance of the error term in the model, is provided by the MSE, the mean squared error, in the analysis of variance table for the regression. Okay, so beta hat cov, again, is the 3x3 covariance matrix for beta hat. Now, from there, I'm going to calculate tcalc. And again, tcalc is the difference between the point estimator of beta 2 minus 0, which is the hypothesized value. And then we divide that by the estimated standard error of beta 2 hat. Now, we get beta 2 hat from the beta hat vector, and beta 2 hat is the third entry in that vector. There's only one column, but we still need to specify both the row and the column in picking out that entry. And so beta hat, and then with the 3, 1 in the square brackets, pulls out beta 2 hat for us. And then from that, we subtract the hypothesized value of beta 2, which again is 0. And then we divide that difference by the estimated standard error of beta 2 hat. Now, we constructed the covariance matrix for beta hat, the vector. The estimated variance of beta 2 hat is in the 3, 3 entry in that matrix, right? And so the entry in row 3, column 3 in beta hat cov is the estimated variance of beta 2 hat. The standard error of beta 2 hat is the square root of that quantity. And so that's why we're taking its square root. So that calculation gives us tcalc, the test statistic for this t-test. And then what we're going to do is calculate the p-value for this test. Instead of looking up critical points, we'll just calculate the p-value. And because this is a two-tailed test, we first have to find the right tail area above the value of tcalc, the absolute value of tcalc, with degrees of freedom for error equal to, in this case, 22. All right, and then we multiply that by 2 because, again, this is a two-tailed test. and then we'll print those values out and use them. All right, so let's just run this and see what we get. Okay, and so we have here the covariance matrix, the estimated covariance matrix for beta hat, but we didn't get anything else. And the reason is because I changed the variable from t to t calc a second ago, and so I didn't change it everywhere I needed to, apparently. And so yeah, so here's where I need to change that. Okay, and let's run that again and see if we get our results printed out. Okay, there we go. And so we see here that the value of t-calc is equal to 3.98, 13131, right? And the p-value for this test is 6.312 times 10 to the negative fourth power. All right, so if we rounded to 4 decimal places, it would be 0.0001, or 3 decimal places, so 0.001. All right, and so we can see here that there's strong evidence against the null hypothesis that beta 2 is equal to 0. And so we would conclude that beta 2 is in fact non-zero, and therefore delivery time does depend linearly on the distance that the delivery driver has to walk, even though the number of cases is already in the model. So that's how we can do this analysis, do this follow-up analysis using PROC IML. Now we can also do this analysis using PROC REG. All right, so I have the same description here. And so let's scroll down and let's look at the analysis that we have to do, or that we can do with PROC REG, and get the necessary quantities for the analysis. And so what I'm going to do here is I'm going to invoke PROC REG, run PROC REG. And again, I don't need to see any plots at this point, so I'm going to suppress that so we can focus on the output that we need to see. And then in my model statement, I'm going to include the option, the I option. And what this does is it's going to display the inverse of the X prime X matrix in the output. All right, and I'm also going to suppress really all of the printed output except that which we need. And so I'm going to do that using the ODS select statement. And to do this analysis, I need the parameter estimates. I need the values in the ANOVA table. And I do need that inverse X prime X matrix printed out. So I'm going to go ahead and print that out as well. Now, let me just go ahead and run that section of the code. And we can see here that we have the parameter estimates table. And in particular, we're going to need the parameter estimate for beta 2. All right, and so beta 2 hat, we can see here in the parameter estimates table is 0.01438, rounded to 5 decimal places. We're also going to need the covariance matrix, the estimated covariance matrix for the beta vector, and that is the upper 3 by 3 portion of this table that I'm circling here. And the estimated variance of beta 2 hat is given by the entry in row 3, column 3. Okay, and so actually I need to back up. That's not quite correct. To get I need to multiply that matrix by sigma hat squared, which is provided by the mean squared error. All right, and when I do that, then that will give me the estimated covariance matrix of beta hat, and then I would use the product of the MSE and this quantity. Okay, that would give me the estimated variance of beta 2 hat. Then I take the square root of that to get the estimated standard error of beta 2 hat. All right, now let's take a look at the rest of the program. And you'll notice that what I'm doing here is I am actually taking the output from the various pieces. All right, so I'm taking the point estimate, I'm taking the MSE, and I'm taking this quantity, and I am creating a new SAS data set by hand, okay, to do these calculations. All right, and so what I've done is I'm creating a new data set called calc, and in my first step in the data step, I'm going to calculate the value of my test statistic. And so here I have the value of beta 2 hat. From that, I subtract the hypothesized value, which is 0. And then on a hand calculator, I calculated the product of the point, let's see, this quantity here and the 10.62417. Already done that. Okay, and I entered that value here just as a literal value. All right, and I have to be sure to take the square root of that, all right, to get that standard error. So that will give me the value of the test statistic t-calc, and then I do the same kind of calculation I did in PROC IML to get the p-value for this test, right? And in this program, I'm actually going to provide or show you the f-test as well. And so I'm going to differentiate the two p-values based on the t-value and the f-value by appending _t and _f for those p-values for the t-calc and f-calc respectively. Okay, and so this is how we can get these calculations for this particular approach. And so let me go ahead and run the program here. And so you can see here that if we focus on the very bottom, these are the results of this custom hypothesis test. The value of t-calc is 3.98131. And the p-value for that test is 0.000631258. And that's exactly what we got, just expressed a little differently, expressed as a decimal as opposed to in scientific notation. It's the same value we got when we used PROC IML. Now, the other thing that we're doing here is we're calculating the f statistic, which is just the square of the t statistic. Okay, and you can see here that the f statistic would be 15.8508, and the p-value based on that is exactly the same as the p-value for the t-test, right, as it should be. So that is how we can do these calculations using the t-test and doing it, constructing it kind of by hand using the output from PROC REG. But let me just point something out here. Notice that the value for t-calc, if we round that to 2 decimal places, 3.98, that is the same exact value for the t-value we have in the parameter estimates table for x2 in the output from PROC REG. The p-value rounded to 4 decimal places is 0.0006, and if we round our p-value to 4 decimal places, we get the same value. And so the bottom line is that this analysis, all right, this hypothesis test that we did by hand, essentially, by obtaining the point estimate for beta 2, by obtaining the estimate of sigma squared, and then multiplying that against this quantity to get the estimated variance of beta 2 hat, taking its square root, and then constructing the t-statistic programmatically in this data step down here. All of that work, that whole analysis is actually being done right here, right in the last row of this table. Okay, so in the row corresponding to the variable x2, it's doing that t-test. All right, and so we really don't have to roll our own in this case. SAS is giving us this result for free, essentially. But that's how you do it. So now you know how to do the calculations, both using PROC IML as well as PROC REG. And so if you wanted to do it by hand, you could. All right, but I guess one could ask, if it's already provided, why take the time to do it? Because anytime you're writing a program, you need to make sure that it's validated and that it's providing accurate results. Now, obviously, we could do the same kind of thing, at least get the required quantities to do the t-test using Minitab. All right, but it would look essentially like this, and you can do it on a hand calculator and so forth. So we're not going to fire up Minitab to show that. All right, so that's all we're going to show in this lecture video. In a subsequent lecture video, we're going to show how to use a different approach, a more general approach, to do this same kind of a test, but that it would generalize to additional tests as well. So I'll see you in the next lecture video.